We've explored how transformers generalize through attention for sequences in case TCM 123005. But what about images? How did this architecture, originally for language, jump to computer vision?
That's a fantastic question. The key lies in the foundational premise of this paper: attention is all you need. It proposed a fundamental re-architecture for sequence processing models.
Traditionally, language models relied on recurrent or convolutional networks. This paper, however, introduced the transformer, based solely on attention mechanisms.
Right, and this was a significant advancement for NLP, especially for tasks like machine translation, which we discussed in #TCM-003001. But vision models felt so different.
Crucially, the transformer explicitly states it is dispensing with recurrence and convolutions entirely. This means it wasn't just adding attention to existing architectures.
So the core idea wasn't to augment CNNs or RNNs, but to replace them. That's a bold claim for any data type, let alone images.
The author saw early that the transformer generalizes well to other tasks, even showing success in constituency parsing. The underlying attention mechanism proved surprisingly general across various sequence tasks.
So the vision was always there that attention could be a general-purpose sequence processor, not just for words?
Exactly. Another significant benefit, as highlighted here, was that transformers were more parallelizable and requiring significantly less time to train. This efficiency applies to any sequential data.
That makes sense. If you can process all parts of a sequence at once, rather than step by step, it's faster. But an image isn't obviously a sequence in the same way text is.
You've hit on the key challenge. Many initially thought images required convolutions because of their spatial structure. The leap to vision meant rethinking what an image is to a model.
So the intuition we had from text that attention connects words needs an update for pixels.
It needs an abstraction. Let's look at how the transformer architecture, and specifically self-attention, works in general before we apply it to images. We'll use this excellent illustrated guide.
All right, how do we build that general intuition for attention that works for anything?
This post, the illustrated transformer, builds the model block by block. At its heart, the transformer uses attention to process input. Think of it like a smart filter.
It's like a filter because it selects and enhances certain parts of the input. But unlike a simple filter, it's smart because its rules for filtering are learned and adapt based on context, rather than being fixed.
A filter? So it's picking out important bits from its input? Is it like a spotlight?
Before we fully enter the encoder-decoder structure, there's a critical mechanism. The transformer processes all tokens simultaneously, meaning it inherently loses the sequential order of words or elements. If you just feed word embeddings, "the animal ate the food" would be indistinguishable from "the food ate the animal."
That's a huge problem for understanding language. Order is everything. How does the transformer keep track of it without recurrence?
It uses positional encodings. These are numerical vectors, often learned or predefined patterns, that are added to the input embeddings. Each position in the sequence gets a unique positional encoding, which provides the model with information about the absolute or relative position of each token. This way, even though the word in each position flows through its own path, the model knows where it belongs in the sequence. Newer models even use advanced forms like ROPE positional embeddings mentioned in the update to this guide.
So the model isn't just looking at what the word is, but also where it is in the sentence. That's a clever way to reintroduce sequence awareness into a parallel architecture.
The transformer itself has two main parts: an encoding component, a decoding component. For language, the encoder reads the input sentence, and the decoder generates the output.
And the connection between them is where attention traditionally comes in for translation, right?
Yes, but crucially, each encoder also has a self-attention layer, a layer that helps the encoder look at other words within the same input sequence.
Ah, self-attention. So an encoder encoding one word, say it, can look at animal in the same sentence to understand it better, like clarifying pronouns.
Precisely. Take the sentence, "The animal didn't cross the street because it was too tired." When the model processes it, self-attention connects it to animal, not street.
That's a clear example of what self-attention does. It's about context, relationships between elements in the sequence. But how does it do that?
If you're familiar with RNNs, their hidden state allows an RNN to incorporate its representation of previous words. Self-attention achieves a similar contextualization, but in parallel.
So instead of a sequential chain remembering what came before, self-attention lets every part of the sequence see every other part simultaneously. That's the parallelization benefit.
Indeed. This illustrates a key property. The word in each position flows through its own path through the encoder. Each word gets its own contextualized representation.
Okay, so the encoder takes a list of word vectors and outputs a new list where each words vector now knows about other words in the sentence. This creates a highly contextualized representation.
While paths are independent and feed-forward layers, this page clarifies there are dependencies between these paths in the self-attention layer. This is crucial for context, but also allows parallel computation, so it's not fully independent, but the dependencies are structured in a way that allows for greater parallelism than RNNs. This hints at the mechanism for images.
So it's not fully independent, but the dependencies are structured in a way that allows for greater parallelism than RNNs. This hints at the mechanism for images.
Exactly. Now that we have the high-level intuition, let's zoom in on how self-attention actually calculates these contextual relationships, step by step.
All right, show me the details. How does it know what to pay attention to?
The first actual step in self-attention is to create 3 vectors from each of the encoder's input vectors. These are query, key, and value vectors.
Query, key, value. This sounds like database lookup, which we touched on before. Is that exactly what it is?
It's a common analogy, but it's more nuanced. As the text states, they're abstractions that are useful for calculating and thinking about attention. It's not a direct lookup like a hash map.
So the lookup analogy might break down. How should I think about query, key, and value then?
Think of it this way. The query is what I'm looking for from other elements. The key is what I have to offer as a match. And the value is what content I'll provide if I match. This analogy helps understand their roles in comparison. But unlike a literal database, these aren't fixed items. They are learned projections. As Maya said earlier, these Q, K, V vectors are created by multiplying the original input vector by 3 different learned weight matrices, often called WQ, WK, WV. So the model learns how to project each input into these query, key, and value aspects.
Okay, so for each input, we get these 3 different aspects of its meaning, and they're created by multiplying the input vector by learned matrices.
Next, we calculate a score. For each word, say thinking, its query vector is compared against the key vector of every other word in the sequence, including itself. So thinking asks, how relevant is every other word, its key, to me, my query?
Exactly. The score is calculated by taking the dot product of the query vector with the key vector. A high dot product means high similarity, high relevance.
Dot product makes sense for similarity. So we get a relevance score for every word pair for a given query word.
These raw scores are then normalized. We divide the scores by 8, then pass the result through a softmax operation. Softmax turns these scores into probabilities that sum to 1.
So now, for thinking, I have a percentage for how much attention it should pay to the, animal, street, and it, etc. They're learned attention weights.
Finally, we multiply each value vector by the softmax score. The intuition is to amplify relevant values and diminish irrelevant ones.
So the value is the actual content or information that's being passed on, weighted by how much attention it should receive based on the query key comparison.
The final step is to sum up the weighted value vectors. This produces the output, a new context-rich representation for that initial word. This process happens for every word.
This whole process seems perfectly general. It doesn't care if the words are actual words or anything else, as long as they can be embedded into vectors.
What we've just described is a single attention head, but the transformer actually uses multi-head attention.
Multiple heads? So instead of one set of Q, K, V, we have several? What's the benefit?
Precisely, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. Think of each head as learning to look for a different kind of relationship. One head might focus on grammatical dependencies, another on semantic similarity, another on co-reference. All of these separate attention outputs are then concatenated and linearly transformed. This, importantly, helps keep the computation of multi-head attention mostly constant relative to a single large head.
So it's like having several experts analyzing the same sequence from different angles simultaneously, and then combining their insights. This increases the model's capacity to capture complex patterns while maintaining computational efficiency.
Precisely. This domain-agnostic nature of self-attention is what made the jump to images possible. Let's see how researchers applied this to computer vision.
Okay, so if an image is just another sequence, how do we turn pixels into query, key, and value vectors?
Before we get into the mechanics, it's important to note that while VIT can achieve excellent performance, it often requires very large pre-training datasets like JFT300M with hundreds of millions of images to match or outperform state-of-the-art CNNs, especially on smaller datasets. This is a practical limitation for many researchers and applications. The original paper title itself implies image recognition at scale.
So the pure transformer approach isn't a free lunch. It trades architectural simplicity for a heavy reliance on data scale, at least in its initial successful demonstrations. And what about computational cost for very high-resolution images, where the sequence of patches could become extremely long?
That's a valid point. The quadratic complexity of standard self-attention with respect to sequence length means that processing extremely high-resolution images directly can become computationally expensive, leading to active research in efficient attention mechanisms like sparse attention or local attention for vision. That's a known trade-off.
So how does this paper titled "An Image is Worth 16 by 16 Words" bridge the gap? Are they literally chopping up images into 16 by 16 pixel pieces?
That's exactly it. The core idea is to transform the image into a sequence. Instead of words, the basic units are fixed-size image patches.
The Vision Transformer, or VIT, takes an image and splits it into non-overlapping image patches, typically 16 by 16 pixels each.
These patches are then flattened into 1D vectors and linearly projected into a higher dimensional embedding space, just like word embeddings in NLP. This creates a pure transformer applied directly to sequences of image patches.
So, a 224 by 224 image chopped into 16 by 16 patches becomes a sequence of 196 vectors, and these vectors are the inputs to the transformer, just like word embeddings, presumably with positional encodings added.
Once we have these image patches flattened and linearly embedded, they essentially become our visual words. But for classification, the VIT paper introduces a special token to interpret an image is worth 16 by 16 words.
A special token for images? Like a CLS token in BERT for text classification?
Exactly. A learnable classification token, often called the CLS token, is prepended to the sequence of image patch embeddings. The CLS token's output state, after passing through the transformer encoder, serves as the aggregate representation of the entire image for downstream classification tasks. It's how the transformer condenses all the information from the visual patches into a single vector to make a prediction.
So it's a dedicated summary token that learns to accumulate the global image information, allowing the transformer to make a single prediction for the whole image, rather than processing each patch individually for a label.
With this, the VIT is relying on sequence processing to infer image-level properties. The self-attention mechanism can now weigh the relevance of different image patches to each other, forming a global understanding of the image content.
So instead of local convolutions building up a hierarchy, self-attention builds relationships between distant patches directly. This is a fundamental shift in how vision models operate.
Indeed, a major implication, which the paper emphasizes, is that this is achieved without introducing any image-specific inductive biases. Unlike CNNs, which are hardwired for local features and translation invariants, VIT learns these properties from the data.
That's why it needed such massive data sets. Without built-in assumptions, it has to learn everything from scratch, but then it gains incredible flexibility.
Exactly. The transformer's ability to treat diverse data types as sequences, combined with the power of self-attention to model long-range dependencies, and the introduction of simple adaptations like image patching and the CLS token, allowed it to leap from NLP to state-of-the-art computer vision. It's a testament to the versatility of the attention mechanism.
So the core idea wasn't to adapt images to CNNs, but to adapt images to the transformer's universal sequence processing. And it worked, paving the way for a new era of multimodal AI.